Thank you, Annette, and also welcome from me to this joint Treesearch and Fibre webinar. And in the Competence Center Fibre, we have a particular theme where we like to develop new characterization tools in order to, of course, in general, address challenges in fiber-based and lignocellulose-based materials, but especially for thermoplastic cellulose-based materials. And so far, we have been focusing on the use of advanced X-ray techniques with the National Infrastructure Max 4, and also with advanced NMR spectroscopy techniques utilizing the Swedish NMR Center. But one opportunity which we have identified is another infrastructure, which is the European spallation source, where neutron scattering will be used in the future to investigate all kinds of materials and hopefully also to contribute to breakthroughs in the field of materials from forest raw materials. So with us today, we are super honored to have Professor Daniel Söderberg from the Royal Institute of Technology in Stockholm. And Daniel is, of course, a well-known expert on fiber-based materials and processing of these kind of materials, but is also a pioneer in using then scattering techniques, both X-rays, but also neutrons. And he has, for instance, also been involved in the European spallation source as part of the scientific advisory committee, which has the task to oversee and develop the science at this new facility. So with this, Daniel, we look very much forward to your presentation.
Yes, first question is, can you see the presentation?
Yes, we can.
Yes, thank you. So thank you, Alexander. So I will talk, you talk about different level of expertise. I'm better in fibers than neutrons. Neutrons is some new possibilities, and I will try to highlight how I have been involved in trying to use neutrons as a complement to X-rays. And there are some good things with neutrons and some bad things with neutrons. But first, I want to point out that we at KTH has reverted to the old logotype without the blue around it. So this is the new old style of KTH. Talking about neutrons, ESS, as Alexander said, is on the way. There are other sources, and we have done things at other sources around the world. The benefits of neutrons are related to the selectivity of what they can see. The backside is it's hard to get time. There are fewer neutrons per crown. If you would be really specific, it's hard to get time resolved measurements with neutrons, but you can still get some. I will explain, try to outline a couple of possibilities where we have really benefited from neutrons. The first one is related not to this, but I just want to highlight and step into this. And I know that everyone knows everything about CNFs, but this is a very old slide that I have. It's 12 years ago. That's a long time. This is a film, so that's a self-standing free film. And of course, that is one possibility to use CNF. Another possibility that we have to try to explore is, of course, if you have films, this is freestanding, you can also consider making films as coatings. So we have been working a lot with spray coating. And the starting point of that is Professor, since last week, Professor Stefan Roth at KTH. Who has been the starting point for trying to do spraying for making coatings of, for example, bio-based material. And the cool thing with spraying is, of course, you can provide barriers. The good thing also is that it's a roll-to-roll industrial process. So it actually is quite scalable. If you can succeed in lab, it's not too far away that you can make larger areas. We have been working a lot with trying to evaluate what happens in films. And to the top right, I will get back to that a little bit later. We're trying to show that we are using a CNF suspension. In this case, we are spraying. I will get the 1 second. I want the spotlight. What we have is then a spray, spraying a nanocellulose film, and then we're using something called grazing incidence with X-rays. You can study the behavior of the film. The interesting perspective is that if you want to do this with roll-to-roll coating, you typically have to build an equipment. So this is quite complicated equipment that actually put into a beamline. So this is PO3 in Hamburg at the Petra 3 synchrotron. You can put it inside. This is a Kapton film that is moving, and then we can spray on top of that one, so you can actually mimic the roll-to-roll industrial process, also using X-rays in this case. So that is one possibility. Looking at what you get if you use X-rays, so going back one step with grazing incidence coming in this case, it's X-rays. We will see the effect of spraying on a surface. The reflection you get from the X-rays will be dependent on the nanostructure of this film. So this pattern that we will see is directly dependent on what happens on the surface. And just to show a little bit of the time resolution you can achieve by doing this. So here we have the spray. We're spraying a film, and we can heat it as well. We can dry it. We can actually see dynamics. So what we'll see is a pattern that changes depending on, now we're spraying a particle with pulses, and then you can also see how this gradually then freezes and becomes a nanoparticle or a nanostructure material. So this is X-rays, and it gives you dynamics. So in looking in this, I will talk about two things. Grazing incidence is trying to use the full field or the full detector image by having an incident beam. In this case, I formulated also that grazing incident scattering. You can do it with neutrons, and you can do it with X-rays. What you will get in grazing incidence is that you get a detector image, and you can use both the lateral and the vertical information to characterize the structure you have in the film. And we can actually adjust penetration depth, and by looking at this sort of behavior, we can look at nanoparticle heights, roughness, or distances and radius of structure. And we'll get back to that throughout the presentation. So just taking this simple sample of spraying some fiber-based material. So this is a spraying of tempo CNF, different charges. So it actually means a couple of things. It means that it behaves differently because of the surface charge. And the second part is that actually morphology of the CNF is changing. By doing this spraying, creating films, you can actually look at the films you get topographically. So that was what we have here. We have, in this case, then 4 different charges. They look slightly different. You can, of course, with AFM start to try to characterize what you see here. But one of the possibilities then with neutrons is that apart from characterizing structure, which you can do, you can characterize things with water. And when we want to characterize, one of the cool things and one of the problems is you need to find a fitting model to evaluate the structure. So starting with this system, we have films, we have some sort of structure. Let's pretend that we're all physicists for a moment. Let's assume that everything is simple, and then set up a model that just it's actually a model that is paracrystalline. It assumes that everything we see in the film, and now I talk about, if you look at the film from the top, you will see, you can see a hole, or you can see fibers stacked together. Let's pretend that when the X-ray comes in, we can depict them all by having these cylinders, and we will choose to have cylinders of a couple of different sizes. So we actually determine that we have a cylinder of a given diameter, distance between themselves, and a different diameter with radius. So we can actually have a set of various sizes. And by doing the grazing incidence, we can take this model, we can fit it to the data, And again, we are fitting now the full field, the full image that we have here. If you then integrate it and look at what happens in, I will go back. If it happens in the Y direction here, we are looking into what happens in the plane of the film as we see it with the incoming beam. What we can see is that we get integrated scattering curves. We can take this model that we have developed and we can fit it. And we can fit it for different charges. And depending on surface charge, we can then determine that we have a structure that depends on, if you look at this, you can fit everything in the curve, almost everything with two types of objects, something that has a large radius and a distance that is about 60 nanometers, and something that has a small radius with about the same distance. So this model of how the structure looks like is kind of good at fitting these curves. So it gives you an insight about some sort of bimodal size distribution in the films. And this is then only looking at material structure. But of course, if we talk about cellulose materials, we are also sometimes interested in water. But it seems water is a problem for most materials. So what happens if you then subject these dried films to water? If we were doing this with the X-rays, we can still do the characterization, but the X-rays will not make any difference between the water, in principle. In principle, no difference between the water and the cellulose. And on the other aspect, cellulose is very close to water, except there's a carbon atom for every water molecule. So it's very hard to differ between the water and the cellulose. So what we did was chose to try to do this with neutrons. And this is, of course, has a little bit to do with neutrons and a little bit with Japan. We don't have ESS, so we went to one of the best sources available, and that is J-Park, which is not so far from Fukushima in Japan. At J-Park, we have a set of PhD students, including Calvin, that was the main and lead author of this. And what we did, except try Japanese food, was try to do experiments with different types of neutron techniques. So there are possibilities to do experiments, and you need to be a couple of persons to do this as well. The only thing I can say, my own experience with neutrons is that it's slower than doing experiments with X-rays. All measurements take longer times. So what can we do now with neutrons instead of using X-rays? We still have a film that is sprayed. The possibility we have now is by using D2O, we can actually use the fact that neutrons treat the hydrogen and the deuterium differently. So it's highly absorbed by the hydrogen and not by the deuterium. So with this, we can actually start to look at what happens if we are adding water with deuterium. We don't see that here, the D2O, we will see these changes in the structure, because in the cellulose, we still only have hydrogen. And by doing this type of measurement, taking the grazing incidence data, similar type of model, we can actually start to exploit what's happening when we're cycling humidity. So with the pristine films dry, we get a scattering. And in this case, we are not talking any longer about the scattering in this direction. We're talking about we're not talking about this direction. We're talking still about this direction. So we're doing exactly the same as with X-rays. And by doing this, we can start to figure out what happens when water enters into the film. What we can see is that we're changing the intensity when we humidify. So we go from the black to the blue. And when we re-dry, we never get back to the original film. So two things happen. First of all, we can see that this type of structure we get when we put in water changes morphology. And the second part is by cycling this, we can see also that the humidification permanently introduces changes to the original structure of the film. So that is possible then by using neutrons. As you know, someone said some. Yeah. Sorry for that. So this is then again, we have been talking about grazing incidents. We are interested in the full field that you can get out of this. Another possibility is to restrict this to only one component that is out of plane or sort of normal to the surface. And then we're working with something called new reflectometry and neutron reflectometry. And by doing neutron reflectometry, we should go back. We will actually try to understand what happens through the thickness of the film. Because then we get something called the neutron scattering length density as a function of our measurement, and that can characterize the density of the material, the amount of material throughout the sheet. So in this case, we have a neutron beam, we have our electrolyte in this case, or actually it's a film. It's mounted into the neutron beam. We are looking at what happens now only out of plane here, so the thickness direction, and what we get then is an intensity curve throughout the thickness of the sheet. So that is really, so this QZ now, which is the inverse, can be translated into what happens, what is the neutron scattering length density as a function of position of our film. Sorry for that. And what we can see in this case is that we again can understand the effects of humidity cycling and see how that affects the density of the film. And by doing all of these things, we can separate water behavior from the dry structure. And then you can start to think about what is the effect of this. I would say that these measurements typically took an hour to do these samples. In reality, if you do this type of measurement, I want to show how fast the system can be. So in this case, we have just sprayed a CNF film on a wafer. And in this case, it's a DS sign that has been used as an imprint. So here we have cellulose. It's cellulose here. There is no cellulose here. So it's just a mask for the spraying. So Kelvin did. And now we will see what happens. Sorry. So this is this. And the only thing that Kelvin does now is he's blowing with his breath on this surface. So humidity just by breathing is changing the thickness of the cellulose films, and it's super fast. And it's of course related to the structure, a nanoscale structure of these materials. How fast does water come into the films? So even if this is a super fast phenomena, that would not be possible to characterize with neutrons, because when we do neutrons, as I said, just to get one of these curves that we have takes an hour. So it's not a tool for dynamic studies on the time scales of milliseconds or seconds. Not in this case. And then you can start to think about why do we use neutrons and water? Yes, we want to understand the structural changes. I want to point out that when anyone is interested, there is an excellent paper, what I believe is an excellent paper that was made quite recently, and that is starting to look at something called quasi-elastic neutron scattering. It is a little bit more advanced technique, needs more material. You can't do this on a thin film, but what you can do is actually use the quasi-elastic neutron scattering to start to think about what is the diffusion of water in a material. And again, they have done this for different types of CNF and bacterial cellulose, and then you can start to understand how does water diffuse in a cellulosic materials. So that makes it possible then to separate by diffusion that happens in the spheres that we saw when we were doing our grazing incidents, and the more slow diffuse motion that can also be seen as a part of the structure in itself. So I suggest this is an interesting technique. It has challenges. We are going to try to do it ourselves, but these are the first that I've seen doing it. And as I said, doesn't work with films. It needs very much thicker objects. So that's two ways of using neutrons. I also think that neutron has an excellent capability to be used for industrial purposes. So now we're not talking about any longer that we want to understand the nanostructure as a potential for future reactive materials. That's the one that we saw with Calvin breathing on this surface coated wafer. We also have been trying to look at what happens for process efficiency, and we're going to look at neutron as a tool for cellulose-based materials for electricity transformers. And the starting point of this is to understand something that I don't think everyone knows. To the left here, we have a high voltage transformer. It's an object that they want about 8 years of lifetime. If you look inside, it contains something called pressboard. A pressboard, that's a cellulosic material that is impregnated with oil. So by volume, you could argue that the biggest part of a transformer is cellulose. And it's typically formed by pressing thick cellulose sheets. So what we see here is produced pressboard. So see it as a paper sheet, but it's much thicker. It's made by having sheets that are pressed together, wet, with a certain force, adding heat. Inside, when you do this, you actually have to add something called wires. And what you do is just you press these together, you apply the heat, and you create a high-density cellulosic material in the center here. And this is a process that is well known. It has been used for a long time. Of course, this really is dependent on energy. How much energy do you consume? And one of the key challenges is to both try to optimize energy usage. So you want to reduce energy demand, save lower carbon emission footprint, but you also want to understand the structure of this material, because the pressboard needs to be very uniform as well, not to induce any type of shortages. Because if you have a structure with, for example, a pinhole, you would risk that the transformer burns, which they do from time to time. So to try to understand this, we start by thinking about what was important. Of course, you have pulp properties that always tends to be important. So the cellulose fibers are a special type. You can't use any type of cellulose fibers. We also know that the fiber network mat that you create is of importance. Temperature when you make this material is of importance as the press load. And you can start to find other, maybe more insignificant, but still important parameters. And then you start to think the next step is, with all of these parameters, what are the physics of this process? And what it is heat transfer, of course, because we try to apply heat. We create steam in the process. And by doing that, we actually generate steam, but depending on the surface properties of cellulose and the temperature of fibers and the temperature at different positions, you can even think that you are generating steam and that you can condense again on a surface. We're also interested in convective transport. Even if we heat something up in the center of the sheet, it needs to be getting out of the sheet and transported away, and that is then the convective transport. And of course, there is some element of diffusion. So it's a set of physical phenomena that is controlling this. And what we did was applied for one of these Vinnova projects within the type of project they still have, that we can apply to a try of neutron and synchrotron-based techniques together with industry. So we applied and got the funding, and then when you got the funding, you really start to try to figure out what you want to try to do. And what we had as an aim was to understand what happens inside this material. Can we see any type of phenomena that is related to any of these physics that we are interested in? So what we did was spend quite a lot of time, and maybe we did not the correct thing from the beginning. We started to design a setup where we wanted to be able to subject a cellulose bed to heat and pressure and everything. We did quite a lot of modeling on this as well, to try to see if we can predict and get a nice design on the system. However, it ended up with another first step, which I always would recommend, reduce the complexity. So all of the first thinking was to have advanced measurement techniques, advanced modeling, but we got an opportunity to talk to Dr. Jeroen Plomp at the TU Delft, and it turns out that in Delft they have a reactor on campus, a 2 megawatt reactor for example doing neutron research. And we came in this discussion with all of our ideas of the more advanced stuff, and then we ended up with that, of course, whatever you need, whatever you do. Can you see the spotlight?
We can see your marker, but not any spotlight.
No, it has disappeared from my screen. So, and the marker, that makes it even more interesting. Let's see if we can. 1 second. Do you still see the marker?
Yes, we do.
Yes, thank you. So we ended up with what is the feasibility of this type of studies? We actually purchased the instrument time through the Vinnova funding. That means that you're not applying for time. It's a little bit faster. We did some measurements for 2 days. We realized that we can't do too much initially with pressure. That requires a lot of safety concerns if you want to work at high pressures. If you at the same time want an elevated temperature, because then it's steam under pressure, and that requires some developments. It ended up with a question that we really want to look at water evaporation and boiling. We want to see what we can actually see in the system. And of course, some sort of what can we extract as data. So instead of this complicated system, we ended up with this very simple wafer design, and that was Jeroen's suggestion. So what we did was, this is a wafer structure made in pure aluminum. So all parts are aluminum, except the bolts. You will get to that. The system is such that in between, in this wafer, we can put in the fiber mat that is wet. We can't apply pressure, but we can put in something called shims, so we can restrict the dimensions, which of course implies a certain pressure. So we can have different volumes with the same amount of fiber. We have a holder so that this sheet doesn't by some means fly away when you generate steam. And we can heat the system. We can take the neutrons, so we can send the neutrons into this and have the detector on the other side and image what happens to this when heating. So it was a very simple setup, and that turned out to be really good. Talk about heating. We didn't choose the most complicated heating mechanism. This is a heating plate. It's a stove that was put in a neutron beam. So you could actually lift it up to get in contact with this aluminum wafer system. And then by using an IR camera, we could actually look that the heating of the aluminum is very, very quick. So this was the only heating we had. Talking about understanding the load you have to the system, this is also no need for calibration. It's just a weight. And this piston just makes sure that the sheet that is put inside, so this is looking from the side, actually doesn't move. So the final experiment looks like this. So now we're seeing neutrons that has passed through our wafer. We are looking from one side, the neutrons comes from the other. We have two cases here. The left one is a 2 millimeter wide slit. So it's 4 millimeter thickness, and we have a shim that is 2. So that's half of this void is now filled with aluminum shim. And the right one is without aluminum shim. So it's the total amount of water plus the cellulose mat to the left is double than it is to the right. And since neutrons are absorbed by the hydrogen, that means that less is passing through. So black means that there is more water present. We can also see that the aluminum is, you can see it a little bit, but the good thing by using neutrons is that the aluminum is an excellent window. It's a good material that doesn't take up so much neutrons, so it works as a window if you're doing any type of other visual experiment. When we start the experiment, we can also see that there are black rings here, and that is in the holes where we have the bolts. There is water agglomerated when we just have rinsed the system. So the first thing that we'll see that when we heat it up is that this water boils away. And now we're going to see two different measurements made at two different times, but with the same time resolution. There is 2 seconds between each image. And we can see that we are heating it up. We can see that water is disappearing from the holes. We can also see that something is starting to happening inside. And we're actually, you can see that it's boiling here even. So all water has to go out through the top. This is then this place holder for the system. We can see that the right one now seems to, something happens, there's a spot here, and what happens is that it dries. And when this has dried, the right one, we still have not dried the left one that had twice the amount of water. Now we can see that it starts to dry eventually at the edges. And it takes a much longer time to dry for the left one than the right one. Sorry. So what we see is that it dries, and we get a spot in the center as well here. And when we reach the total, all water is taken away, we can see that the amount of cellulose is actually the same. So the only thing that differed when we started was that we had about twice the amount of water in the left one. And at the end, we can only see the cellulose because it's hydrogen there. It's the same amount of cellulose, so we can actually see also a little bit of the structure of the material. Just to point out something that happens in the end when drying. So please have a look at the right one. Look at the edge when we're drying now. So we have water still here. This is dry. And then now all water is gone. And the last thing that happens is that this piece of cellulose actually also shrinks. So we can study the shrinkage of the material. So then you can ask what can you get out of this? Then comes the part that will be in the exam for this seminar. There is actually models, and this is nothing that we did. We just took it from literature, but this is boiling because that's what we're studying. We have a static porous media, since we're not dynamically compressing it, but we just have the same amount of fibers. It's kind of static, it's porous. And then you have a set of equations describing the boiling, which means that you have both water and you have vapor, because you can have the different phases. You can have you can have a vapor phase and you can have a liquid phase. If you take all of this, you can actually take the measurements that were done, very simple measurements, it's a 2D measurement, so that is of course contains information what happens because we have a shrinking blob in the center. But if you evaluate the drying of it, you can actually take the measurement and extract data for modeling. So when we have the measurement, we knew that the amount of neutrons is proportional, that we detect is related to the amount of water we have. So by this, we can actually normalize it such that we can measure the exact amount of water and fit the model as depicted to what we have seen in the image. Just as an example of the alternative is to just look at pure boiling, then it's just linear with time. So you supply heat, water evaporates. It's all about the time spent heated. But by doing this modeling, we can actually start to extract data and parameters. So some of the parameters here for the different phases can be extracted by fitting the model. And as doing this, we can actually see that next steps would be to develop this and include dynamic features. And you would like to go so far that you could develop a model that can be used for controlling the industrial process. All of this based on that neutrons will give you a possibility to measure something that is almost impossible with any type of other technique. So the conclusion from this study was that neutron imaging was an interesting technique. It was inoperandi. The time dependence and spatially varying means that we have a lot of data that helps us of extracting parameters. A little bit cool what you can look at shrinkage of paper webs. We can even look at structure of the final material, and we are together now looking at a continued project to take this further with also the dynamic system of pressing, as I said. So that is 3 things that we have done with neutrons. It can be used for fibers. It's super good if you want to differ behavior, separate behavior of water or not. And as a last point, I just want to throw this in, Alexander. We have, please apply to Formax if you have ideas. And if you're interested, you can also always discuss with Alexander what you should do. He's always available to answer your questions.